Is it going?
Hey Holly, Raven. Do you have a pencil from the other day?
I think it's
recording. Yeah, sure. I do have one more pencil.
Okay, where did we leave off? Today?
I like your hair. Hey, you're not sitting next to me today.
Thank you.
Just like,
It's pretty. I don't know if I'm gonna speak.
me too.
Yeah, you guys, oh, I don't think I had a CD chart for this class. Anyways, everybody can sit wherever they want. I think I got it all figured out. Did we figure out the vapor pressure of water at 20 degrees? You gotta look it up in the back of the book. In the vapor pressure chart. Did we do that? I think it was the end of that problem we were doing. So we did the problem of, we didn't do that. I think we just ended with
Well, you were like finishing up the problem as the bell rang, but
the calcium carbonate one that ended with 22.3. Okay, so I didn't do the gases with water displacement. Okay. First off, gases that are not at standard temperature and pressure, in order for these rules and laws to work, we have to first convert them to standard temperature and pressure. You guys understand that? Okay. All right, so we're going to talk about gases collected by water displacement. And so what happens then is if you'll collect a gas, you'll have like a beaker, or usually it's a syringe or a tall cylinder of this, and it'll be filled with water to like right here. And then you'll collect some sort of a gas, you'll have some reaction going on here, might include some fire, I don't know. And then the gas that's produced goes in here, and then the water is pushed down, and then you'll get it like that. You'll get it at a new reading, and then that tells you how much gas has been put into the tube. Does that make sense? That's how they do it. Whether it makes sense or not, that's how they do it. And so when you are measuring that gas, we have to look at the pressure that is exerted this way by the water. It's called water vapor pressure. And so in order to get the pressure of just the gas, which is called the dry gas, without water vapor as part of it, you have to subtract out that water vapor pressure that is part of this reaction. And in order to do that, there's a chart in the back that tells you what water vapor pressure is under certain temperatures. So, so the problem will read something like this. A gaseous product is collected by water displacement. The volume of this product is to be determined at 23 degrees C and 752 millimeters of pressure by a mass gas volume calculation. So the ones that we were doing prior to this were all volume calculations, and now we're going to look at mass volume calculations. Okay. So the one we did last time with the calcium carbonate, the solid, that was a mass volume calculation. Okay. So we have the volume. You want to determine the volume, and the what you're given is the temperature equals 23 degrees C, pressure equals 752 millimeters of mercury. So first we have to do the volume at STP. So we're going to figure that out first. So the V2 at 23 degrees C and 752 millimeters is going to equal the volume at STP times 760 millimeters divided by 752 minus 21 millimeters times 296 K over 273 K. Does that make sense? So the volume that we want to know is going to be a standard pressure volume if we adjust it for pressure and temperature. Does that make sense to everybody? If not, you can look at it. We just took your V1, P1, T1, V2, P2, T2, and solved it for V2. Okay. So that would be V2 equals V1, P1, T1 times T2 over P2. And that's what all those are. Make sense? Okay, so, yes.
Where did the minus 21 come from?
752 minus 21, it was, oh, the 21 is the water vapor pressure. Sorry. Yes, I meant to even point that out. If you look at Appendix 8, Appendix Table 8, the water vapor pressure at 23 degrees is 21.1. So that's what that is. Okay, so what volume of oxygen collected by water displacement at 20 degrees and 750 millimeters of pressure can be obtained by the decomposition of 55 grams of potassium chloride? So, we want to know volume of oxygen. Collected by water displacement, so that tells us we need a water vapor pressure. So we just, as soon as you see water displacement, you just put that in there because you know you're going to have to find out what it is. Otherwise you're going to forget about it like I just did, and if I wasn't copying it out of the book, I would have messed it all up. 20 degrees C and 750 millimeters of pressure and 55 grams of potassium chlorate. Okay, so we do the chemical equation for this. It's going to be 2 ClO3, which is a solid. It's going to decompose to give us 2 potassium chloride solids plus 3 O2 gas. Okay, we're given 55 grams of this, and we want to know how much oxygen. Yes?
Sorry, is this a new problem or does this have to do with this problem?
No, this is brand new.
Okay.
actually, this is a problem that is going to apply that, and it's gonna use the same numbers, but that was never really a problem, it was just an illustration. Okay, so we have 2 moles to 3 moles. This is a solid, so we can't put that in the equation thing. And we can use this one because we're gonna change it from a solid. Okay, so 1 mole of potassium chlorate equals 122.6 grams. Okay, so if you add 3 times 16 chloride and potassium, whatever they are, add them all together, you're going to get 122.6 grams. And then 1 mole of O2 is what? 1 mole of O2 would be what? Gas. 1 mole of a gas is. Right. Remember, if you need a number, just grab 22.4. Okay. So if we do a solution by moles, we're going to find out how many. We're going to find out what we need. So X equals 55 grams of KClO3 times 1 mole, 122.6 grams times 3 moles of O2 to 2 moles of KClO3 times 22.4 liters in 1 mole. So these moles cancel out, these moles cancel out. KClO3 cancels out, grams cancels out, and so you end up with liters of oxygen. And then when you do all the math, you get a number, 15.1 liters. Okay.
How did you get that equation?
Okay. This is the same equation that we were doing before, only this is the new part. This is the changing the mass, because we have a solid. Okay, so we have to do, we're going to change it from grams into moles. Okay, so we have 122 grams per mole. And we want to do that so that we can use our mole ratio, like we did before, to figure out the amount. Okay, so here's our mole ratio. And then that's the ratio. This is the solid in moles. This is the gas in moles. Okay? So we're relating kind of using Avogadro's number, the amount of particles here, amount of particles here, and we're trading them from grams and liters into moles. So we made a common unit that we can compare them with, and then we did the problem that way. Does that make sense? Okay, let's try it again. So do you remember how we can get a mole this way? Okay, so a mole is contains this many grams from the periodic chart. Okay, so that's a definition. And we do that because we want to get rid of grams of KClO3. We don't want that. So if we use grams, we can get rid of grams. And then, if you use this molar ratio, we can get rid of the KClO3. So now we just have the 55. What does our answer want? It doesn't want? I forgot to write that down. It says, what volume of oxygen? Oh, there it is. What volume of oxygen? So we're gonna want liters. So then, we have to have liters here for moles. So this mole will cancel out with that mole. This is our ratio. So if you don't know how to do the problem any other way, you can just do it, figure out what you need by the units that you need to get rid of. So that's another way to do it. Does that make sense? Okay. So we're just changing this solid into moles. We're changing this gas into moles. Then we're relating the two by our molar ratio. And then we can get our volume. And it also works because everything cancels out to give us the correct units for what we're looking for. Okay, but that is not the end of the problem. This is at STP, at standard temperature and pressure. So now we have to go over here and do this problem right here. And the only difference between that problem and this problem is that this is 20 degrees instead of 23, which changes this number. Instead of 21, it makes it 17.5. Instead of 752, I think we have 750 millimeters of pressure. And our temperature is 293 instead of 296. So it's essentially the same kind of problem. Yes?
Would you explain where you got the 17.5 again?
Okay, 17.5. Water vapor pressure. See this right here? We need to figure this out. So if you go in the back of your book, table 8, you look it up for 20
Does
degrees.
this problem relate to this problem at all? Do they have anything to do with each other?
That's the second half of that problem.
That's the second half.
Yeah, this is where we're going to go next.
Why are you doing this? I mean, like, what are you looking for when you do this part of the problem?
We want to change it from, those are good questions, don't laugh. Standard temperature and pressure. Now, we've got this at standard temperature and pressure, which allowed us to do those mole ratios. Okay, so now the actual question was, at 20 degrees, at 750 millimeters of pressure. That's the actual question. So now we're going to do the actual question part over here. So all this is changing V2. We want to get V2. V1 is at standard temperature and pressure. So it's our same problem here. V1, P1, T1, V2, P2, T2. Okay, so we want to know our new volume. It's not at standard temperature and pressure from the one we just got at standard temperature and pressure.
Where's like the 15.1 liters come into play? Like, why do you need it for that equation? Or do you not?
Oh, it's this right here.
Oh, so that's, oh, okay.
Oh, so you're fake. Oh, okay.
What's the 293?
293,
Where's that come from?
it came from right here.
Okay.
We'll finally get to the end. It's been a long time since I've taught. So I'm relearning and teaching at the same time. So your questions are all very, very good questions. Okay, are we all together now? Okay, so what we just did is, if we figure this all out, then we end up with 16.8 liters. So V2 is going to be 16.8 liters. So instead of 15, we get 16.8. This particular temperature and pressure. Okay, the last section in 11 has to do with the gas constant, and I don't know if we'll get through this, but anyways, this is where we're gonna end up. So PV equals nRT. And when somebody told me I was gonna be teaching something about the ideal gases and all that, first thing that popped into my head was that. And it's the last thing I'm gonna do. But anyways, that's where it all boils down to. I've always remembered this, and from that you can get all that other stuff that we've already done. R is the constant that you always use. It has a value of 0.08, which I don't remember, 2057, blah, blah, blah. And the units are liter atmospheres per mole Kelvin. Okay? And that is your gas constant. In your book, it goes through how to figure that out and relates it all together. And shows how you can actually get to that constant. But that is the constant. And N is number of moles here. Temperatures in kelvins, atmospheres is pressure, and liters is for volume. And so what you can do with that is, say you have an unknown gas and it's examined at a particular temperature and pressure, and you get some measurements, you can calculate using this constant and that equation up there to figure out the moles per liter of the gas. And once you get that, you can figure out the mass that you have and therefore the molecular weight. Once you have the molecular weight and you know what the compounds are, you can start to come up with a molecular formula of this unknown gas. So let's go through that and see if it makes sense to you. So we're going to take measurements of oxygen at, let's see, we're going to measure oxygen, the density at a low pressure. Never mind. We're going to start with the properties of an unknown gas at a temperature of 28 degrees C and pressure 740 millimeters. And we find out that the mass of 1 liter equals 516 grams. Okay, so we've got that figured out under those conditions. And we want to figure out the molecular weight of this gas. Okay, so if you just read that problem right there, it sounds pretty hard. I think it does anyways. So if we use this formula, PV equals nRT, it works out a little easier. So 273 plus 28, this is going to give us 301 Kelvin. And our volume is 1 liter. It's right here. So volume equals 1 liter. Pressure is, here is in atmospheres. So we're going to convert our pressure to atmospheres. And that is 740 over 760 millimeters per 1 atmosphere. And so that's going to give us 0.974 atmospheres. And and then our formula PV equals nRT. So, we're trying to figure out the number of moles. So we're gonna have N equals RT divided by PV. And so if we plug everything in, we're gonna say 0.082 times 301 divided by I forgot to put my units in. Why do I have this backwards?
Wouldn't it be PV over
Yeah.
RT?
It would be. Sorry about that, guy. Okay. So it's, atmospheres times 1 liter over, this is 0.97. .974 atmospheres over 0.0821 L ATM over mole K times 301 K. This cancels, atmospheres cancels, and moles comes up here, and liters cancel. Okay, so we're gonna end up with 0.974 times 1 over 0.0821 times 0.301 equals 0.0394 moles. Okay. Okay, then the last part is 1 mole times 516 grams divided by 0.0394 moles equals 131 grams. That's it.
Why did it smell like that 10 hours ago? Oh, I fell asleep with my TV on, so I woke up at 7 a.m. and it says, it was Good Morning America, and it says, snow day! And I was like, yes! But it was like for like Minnesota or something. I was so disappointed.
That's depressing.
It is snowing, guys.
Yeah, and then I checked Indiana News Center, and it was like, there are apparently no